At some point in your life, you've probably seen chemicals represented as balls, spheres above my head, connected in some random globulous kind of Mickey Mouse head shaped things and weird other caterpillar like structures, all with these like balls stuck together. Well, how did they make those and why did they use those to represent molecules? That's what you're going to learn in this video. We're going to learn how to create these 3D models from Lewis dot diagrams and then how we make them look all spherical and stuff like that. By the end of this video, you should be able to recall past key facets about covalent bonding and Lewis dot diagrams in order to apply it to the ability to make 3D models. So the premise for the whole 3D model is really quite simple. You're just starting with something like H2O, so your chemical formula, and you're also drawing a Lewis dot diagram showing where the electrons are more localized, and then you can take that information and create spheres. Notice that some spheres are drawn larger than others, and the reason for that all has to do with electron density, where the electrons prefer to be around which atom. So in other words, in the spherical 3D model of water above my head, you'll notice that the red sphere is quite larger than the white spheres. And we know that that red sphere has to represent oxygen because it has all the electrons around oxygen. Oxygen is more electronegative. It has the higher electronegativity. Therefore, it prefers the electrons to be around it, making the electron cloud or sphere around oxygen larger. Therefore, we draw its sphere larger. Let's try it with some HCl. HCl is its chemical formula, and the next thing we want to do is draw the Lewis dot diagram to figure out which atom the electrons are spending more time with. Who do they want to hang out with? HCl has one H atom, and as we know from the past, H has one valence electron. You can also look at your periodic table for that. And there's one Cl atom. And chlorine has 7 valence electrons. Again, look at your periodic table if you need a refresher on that. Clearly, chlorine is more electronegative. It has more electrons around it, therefore it's happier with electrons being on it. So what we would do is draw a sphere that's larger for chlorine, attached to a smaller sphere for hydrogen. Something like this. And voila, you have a beautiful 3D model of hydrochloric acid, HCl. Let's try it with another chemical. How about NH3, commonly referred to as ammonia, if you watched my previous video on how to name covalent bonds. I've already drawn the Lewis dot diagram for you here, and it's all cleaned up and ready to go. Hopefully it's easy to see that nitrogen even has a lone pair of electrons on it. So it is pretty electronegative, especially in comparison to hydrogen. In this case, your one nitrogen atom would be quite larger than your 3 small hydrogen atoms. Let's try it. And there you have it. We have N in the middle being our larger sphere, more electronegative atom, and 3 small red spheres to represent our hydrogen atoms. Pretty simple, right? So the method I just showed you is kind of qualitative. It's based off of your eye. I mean, you could make one atom gigantic that's electronegative and another one really tiny. You don't really know what the true electronegativity difference is between the atoms unless you do a small calculation. So if you want to be more precise or more quantitative in terms of drawing your spheres for a 3D model, we need to know how to find the actual electronegativity difference between 2 atoms. En, or electronegativity, determines the difference between how equally or unequally 2 atoms will share electrons in a covalent bond. So if the atom types present are 2 or more nonmetals, we know this as a covalent bond. Metalloids do count as nonmetals. And by applying a calculation using these numbers that are predetermined for electronegativity of an atom, we can determine the difference between 2 atoms that are bonded together and see whether or not they're a polar covalent bond or a nonpolar covalent bond. You'll also be able to use this method to determine if something is an ionic bond in a future lesson. For now, you should know that 0.5 to 1.7 as an answer indicates a polar covalent bond. Anything that's between 0 and 0.5 as your difference answer would indicate a nonpolar covalent bond. Just to remind you from periodic table lesson way back when, here's the electronegativity trend you should know. Electronegativity increases as you go across the periodic table up to fluorine. Fluorine is the most electronegative atom on the periodic table with a value of 4. You'll always be given these values. I doubt anyone will require you to memorize them. You just need to know how to subtract the two. So for a polar covalent molecule, as we've talked about in the past, this means that it is a covalent bond, all nonmetal atoms, where the nonmetal atoms are not sharing electrons equally. So there's a bit of an unfair tug of war. The electrons get to spend more time with one atom than the other. This difference ends up being between 0.5 and 1.7 typically. The bond, for example, between hydrogen and oxygen in water has a difference of 3.44 for oxygen and 2.20 for hydrogen. That's a difference of 1.24. That falls within our range of 0.5 to 1.7, therefore we know that water is a polar covalent molecule. And in this case, since we know that oxygen is a larger electronegativity value of 3.44, the oxygen will get more electrons, therefore have a larger sphere and a partial negative charge. So if you're going to draw the 3D model as is above my head, you can see that the 3.44 is roughly equivalent to the size in comparison to the hydrogen atoms at 2.20. How about for a nonpolar covalent molecule? Well, we know that nonpolar covalent molecules are again all nonmetal atoms present, but they are sharing electrons equally. So there's a tug of war with yourself, with your clone, essentially. The electrons get to spend time with both atoms equally, and this difference ends up being between 0 and 0.5. Whenever you have carbon and hydrogen bonded together, you can always know that that is a nonpolar bond, no matter what. If there's a carbon with hydrogen, that carbon-hydrogen bond is nonpolar. Also, as a reminder from a previous lesson, if you have dipole arrows that cancel out, or you can think of them as vectors like in physics, if they cancel out, that also creates a nonpolar molecule. So if we're looking at methane, for example, cow farts, CH4, the bond between carbon and hydrogen is 2.55 minus 2.20. So C minus H, you always just take the larger number minus the smaller number. 2.55 minus 2.20 is 0.35, and that happens to fall within our range of 0 to 0.5. Therefore, we know that methane, CH4, is nonpolar. So using the values above my head, go ahead and pause the video now and try and figure out what kind of electronegativity difference, i.e. the subtraction, you would get with N and O, and figure out if it's going to be nonpolar covalent or polar covalent. Hopefully you saw that O is 3.44 and N is 3.04. When you subtract, you get 0.4. This falls within our range of 0 to 0.5 for nonpolar. Therefore, any molecule with a bond of NO, that bond specifically between N and O, is nonpolar covalent. How about H and F? Give that one a try. Pause the video now and try it. Using the numbers we've been given, we have F here and H here. So we're just going to take the larger value, 3.98, and subtract it from the smaller value, 2.20, to get 1.78. Since that falls within our polar covalent range, we know that HF, or any bond of HF, is a polar covalent bond. How about S and O? Well, S and O are conveniently right next to each other, and we're going to take the larger number minus the smaller, so that's 3.44 for O, minus 2.58 for S, and that gives us 0.86. 0.86 is still larger than 0.5, so we would assume that this is more on the side of polar covalent, even though it's pretty close to the nonpolar range. Okay, so then what about O and O? What if we just have two O's together? O2. So that would be 3.44 minus 3.44, which just gives you 0. A 0 means nonpolar covalent. That would also mean that they're sharing electrons equally with each other. Check yourself before you wreck yourself. Make sure you understand what this lesson was all about and make sure you can actually apply what you just learned. So try and answer these two questions. Is this molecule bonded via covalent bonds, MgCl? And if so, how do you know? If not, how do you know? Either way. Second question, draw the Lewis dot diagram for the following molecule of HF and determine if it's polar or nonpolar. Explain why. and see if you could explain in more than one way now as well. If you'd like the answer to these questions, please ask for the answer in the comments below and I'll be happy to oblige. Otherwise, be sure to hit that thumbs up before you leave me and subscribe to my channel. Hope to see you soon and keep it quacky.
No ducks, no glory.